Math 2414, Calculus 2. Calculus 1 review, integration rules. Full disclosure, there are more than 16 integration rules. In fact, if you look at the back of most calculus books, there is a table of integrals, which often reaches into the hundreds. And I don't just mean 100s, which would be silly to try to memorize all, but there are some that you just need to know. And for the most part, these are just derivative rules backwards. There are some changes, but a lot of them are just derivative rules backwards. And remember that an indefinite integral, an integral without limits of integration, is basically asking what's the antiderivative. So anytime you're taking an indefinite integral with no limits of integration on the integral sign, you should be asking yourself, whose derivative do I take to get this? Now, sometimes it's obvious, sometimes it's not, but let's just get right into it. Most of these I'm just going to put up here. I might make a few comments along the way. Let's start with one of the most important ones, and one of the more powerful ones, pun intended, the integral of some variable raised to the nth power. The integral of u to the n du. And there's a reason I'm using u instead of x when we review substitution. The driving force will be which of these integrals can we convert our current integral into with the correct substitution. To integrate something raised to a power, you leave some space in front, you leave the base alone, raise the power by 1, and then multiply by the reciprocal of that power. Now, be careful because that's an antiderivative of this, but it's not the only one, because there could be some constant that could have disappeared upon integration. So every one of these will have that dreaded plus c. Anytime you do an indefinite integral, you should bring along a constant of integration, because remember, we're looking for something whose derivative is this, and any constant would have disappeared upon differentiation, so any constant is allowed there. Now, some books will write this as u to the n plus 1 over n plus 1, and that's perfectly acceptable. But my personal preference, I prefer my constants in front of variables and not under them. So instead of writing it over n plus 1, I'll usually write it as 1 over n plus 1 times. But if you put it underneath, that's okay. Now, this rule is correct except one time. The time where the denominator is 0. So this is assuming that n is not equal to -1. Because if it is, it makes this denominator 0. There's a special case for n equals -1. If you have a -1 power, if you have u to the -1, that's the same as 1 over u, so that's what the second rule is. Gee, whose derivative looks like this? Natural log. But when you're integrating 1 over u, its antiderivative is actually natural log of absolute value of u plus a constant. If you leave off the absolute value, it's not a horrible crime, but it is technically wrong. So I may call you out on it if you leave the absolute value off when you find the antiderivative of 1 over u. Oh, by the way, these need to be memorized. I would make flashcards. Write the integral on the front, write the antiderivative on the back, and make sure you got them down. Number 3, integral of e to the u du is easy. What do you take the derivative of to get e to the u? Answer, you take the derivative of e to the u, and then maybe some stray constant. Now the b to the u is a little bit different. We did have a derivative rule for that, but the integral of b to the u, where b is any other base, and I should remind you that the base is not equal to 0, but it's greater than 1. Excuse me, got that backwards. The base is greater than 0, but not equal to 1. When you take the derivative of this, you leave it alone and you multiply times the natural log of the base. To take the antiderivative, you leave it alone and you divide by the natural base. You divide. When you take the derivative, you leave it alone and multiply by the natural log of the base. When you take the antiderivative, you leave it alone and divide by the natural log of the base. Of course, plus c. Let's see, number 5, antiderivative of sine. What do you take the derivative of to get sine? It's not cosine because the derivative of cosine is negative sine. The antiderivative of sine is negative cosine. Negative cosine u plus c. What's the antiderivative of cosine? That's like asking what do you take the derivative of to get cosine? You take the derivative of sine to get cosine. So you have to watch your positives and negatives there, but again, to keep them sorted out, number 1, know your derivative rules, and number 2, remember the question is, whose derivative do I take to get this? Whose derivative do I take to get secant squared? Tangent. Careful, whose derivative do I take to get cosecant squared? It's not cotangent. The derivative of cotangent is negative cosecant squared. So the derivative of negative cotangent is positive cosecant squared. Again, the trick here is watching your positives and negatives. But again, if you remember, you're asking whose derivative do I take to get this, and you know your derivative rules, then you can adjust as necessary when the signs are incorrect. What's the integral of secant u tangent u du? Whose derivative do we take to get that? Secant. Don't forget the plus c. Whose derivative do we take to get cosecant u cotangent u? It's not cosecant, but negative cosecant. Because again, the derivative of cosecant is negative cosecant cotangent, so the sign is incorrect. And so the derivative of negative cosecant would give us what we want. Now, if you're not familiar with hyperbolic trig functions, then these might not come to you right away. But if you watched, I believe it was the 5th video in this series where we reviewed the derivatives of hyperbolic trig functions, I did mention, excuse me, that the derivative of hyperbolic sine and hyperbolic cosine are each other. The derivative one is the other. And so they're each other's antiderivatives. The antiderivative of hyperbolic cosine is hyperbolic, antiderivative of hyperbolic sine is hyperbolic cosine. Antiderivative of hyperbolic cosine is hyperbolic sine. And we could come up with some more integral rules for hyperbolic trig functions like we did over here with circular trig functions, but I'll leave it up to you to make those rules. I don't think we'll see them too terribly often. Now the next two are not antiderivatives that we can answer by just asking whose derivative gives us this. For example, whose derivative gives us tangent? Now if you're thinking secant squared, you're thinking backwards. The derivative of tangent is secant squared, but what's the antiderivative? For reasons which we'll review when we do integration by substitution, the antiderivative of tangent is the natural log of the absolute value of secant of u. Plus a constant. Let me check something real quick. See how this author does it. Yeah, that's what he says. That's what I say too. There's an equivalent answer, negative natural log of cosine, but I prefer this one because it doesn't have a negative. They are equivalent though, trigonometrically. What's the integral of cotangent? The integral of cotangent is natural log absolute value of sine. And if you're wondering where the natural log come into play, when we get into substitution, you'll see. Hint, you need a trig identity to rewrite these. What's the integral of 1 over u squared plus a squared? Well, this kind of looks like the derivative of something. When we did the derivative of arc tangent, it was 1 over x squared plus 1. Well, we're using u instead of x, so we can call this u everywhere. But that still doesn't quite match it because now it's got plus a squared instead of plus 1 squared. Well, we can do a little bit of algebraic shenanigans and do a derivative of here with the chain rule and eventually figure out what this is. But I'll tell you right now, it's just an arctangent. Just an arctangent. Specifically, it's 1 over a arctangent of u over a. And again, we could do some smoke and mirrors to make this appear. In other words, connect what we know about derivative of arctangent to create the antiderivative of this guy. But this is something that will show up often and needs to be memorized. As does this one, which looks like the derivative of arc sine, except it's not quite, because if you took the derivative of arc sine of u, it would be 1 over the square root of 1 minus u squared, and this has an a squared there. But again, we could play some smoke and mirror games, some hand-wavy math, and make this work. But it's just going to be arc sine of u over a. Now this does have the stipulation that the a is greater than 0, but don't worry, when you square root a number, you rarely just think of the negative root instead of the positive root anyway. I do know, I want to share with you one problem I always had, and to this date still have if I'm not paying attention, with both of these rules. I know it's u over a, that part I remember. The thing that I always struggled with is when is the 1 over a in front and when is it not? You can just memorize this, and if I sit down and reinvent the rules, then I can go, oh yeah, that's why it's in front there. But when it comes to just a memorization issue, having the 1 over a here and not having the 1 over a here is just something that I always had to really focus on to make sure. In fact, you might have noticed me glancing over here at my integration rules, making sure that I wrote them down correctly. All right, so here are 16 integral rules, some of which will occur more often than others, all of which need to be in your arsenal of things to know. And when we go over substitution, which we're going to do in the next few videos, I'll actually show you where these two come from in case you forget them, because they're actually really easy to re-derive.